Hello and welcome back. In this problem, gas air trapped in a piston cylinder device is being heated from a given initial temperature, initial condition, to a final temperature of 1000 Kelvin. And we are to find the heat transfer and the boundary work that is taking place during the process. Of course, we can see heat is going in and boundary work is coming out, so they're both positive quantities. This is a case of a closed process. As you can see, the system is definitely closed, and it goes through a process, meaning that there is a definite beginning state and end state or final state of this unsteady process. The system is uniform because at any given time the system can be represented by a single state. We'll do a energy and entropy analysis of the system. So let's begin. We'll launch an appropriate test calc. We have already logged into the thermofluid site, and this is a case of closed process. So we follow the system closed generic process, and the problem says that this is a gas, so one of these gas models should be used. It instructs us to use the PG model. Click on the HTML5 and that launches the test calc. Okay, so what are known about the problem? State 1 is our beginning state. Air is already the fluid chosen, so we don't have to change that. And air is at 200 kPa, 300 Kelvin, and we have 1 kg of air. Mass is also known. So the state is completely calculated. And then it's heated at constant pressure. So we know it's a closed system. So first thing first, closed system means mass is not going to change. And they have told us that pressure doesn't change. But we need one more property, and that is a thermodynamic property. That is, the final temperature is given to 1000 Kelvin. Note that the leading zero doesn't bother. It's just to make it easier to type in default numbers. So state 2 is completely calculated. So we know the two states, the beginning and final state. And now to find the heat transfer and boundary work, notice we can use the energy equation. First of all, heat transfer depends on change in energy of the system, the delta E, and also the boundary work, because even though there is no shaft or electrical work, WO is 0, there can be boundary work. And we know the boundary work for a constant pressure system. So let's start with the boundary work. So let's call it WB out. The amount of boundary work that is coming out is what? M1 star, the change in volume. So V2 minus V1. So this is the change in volume, and the pressure is constant in this problem. So P1 equals P2. I can choose any of them. So change in volume times pressure is really the boundary work. And when I hit the calculate button, it is shown in the output area. So about 200 kilojoule of boundary work is performed in this problem. How much has been the energy gain? Delta E. Delta E equals mass times the final energy minus the initial energy of the system. So therefore this is, so we see that there is 501 kilojoules of energy gained by the system, and the system has put out 200 kilojoules of work. So how much heat must be going in? Q in must be supplying both of them. So Q in going in is causing the delta E to rise, and it is supplying enough energy for the system to do boundary work. So these two together constitutes how much energy is going in. So we have calculated the boundary work, the rise in energy of the gas, and the energy in 702 kilojoule.